has finite entropy, it should stop decaying and start oscillating. The reason it starts oscillating is because in a finite entropy system, the two-point function is a sum of oscillating exponentials, and that type of a function, a finite sum, or let's say absolutely convergent sum of oscillating exponentials, can't really go to zero at any time. At any time it can be small, but it has to be oscillating. The value that people throw around for this sort of oscillating floor is a value which is about e to the minus x. So the wiggles or scale about e to the minus x. And so the transition here happens at a time of about x. If they assume that the two-point function is decaying exponentially for a time of order of entropy, it will get down to a size of e to the minus x. After that point, your method oscillates about this floor value. Okay. Yeah, I wanted to present an argument for the e to the minus x, but maybe I'll do that if I have time. If I don't have time to do the lecture today. Let's see. Yeah, sorry, this is g of t. Which is actually, this is interesting. This is that this is a case where it's slightly different to consider a pure state theta and a thermal ensemble. And the answer that one expects for a pure state is actually larger. It's e to the minus x over 2 for this final fluctuating floor value. Right. Let's have absolute value. Well, let's have a real part. We could go for the absolute value, but then it's not from negative. Okay, so this has been a brief introduction to two-point functions. The thing I want you to remember is that we expect them to decay, expect them to decay exponentially. We can analyze it in perturbation theory, and we get a very slow decay, but we can't analyze very well, even if it perturbatively is annoying. Okay, the other aspect of thermalization that I'm going to discuss a little bit is this idea of a quench. So the two-point functions are diagnosing what happens if we take an equilibrium system and perturb it a little bit. And the question is asking a very different question. It's asking what happens if we take some state and excite it all of a sudden to some very high energy, very non-equilibrium state. So a model for this is a state Q, which is given by product over X of some operators acting as like X on the vacuum. So if we have, let's say, a lattice version of the system, then we can act in every site of the system with some local operator OX. Because we're acting everywhere in the system, we're going to raise the energy by an amount that makes sense. We're going to turn this low energy vacuum state into a high energy thermal state. But it's going to be a very special kind of high energy state where all the quanta are sort of uncorrelated with each other. You have created them all out of nothing, independently at each site of the system. And then what happens under time evolution is they interact and collide, and the correlations become more non-local. There are two different types of quantities that one can imagine computing to diagnose the approach to equilibrium of this state Q. The next one is to consider the entropy of a subsystem A of the function of time. So H equals 0. We just acted with these local operators. Actually, let's imagine local unitary operators on the vacuum state. So H equals 0. The subsystem entropy will be the same as what we have in the vacuum. So H equals 0. It'll be the same as we have in the vacuum. But who can give me an idea of what type of entropy we should expect to have for a subsystem in the vacuum state? So suppose we have some region, is there some geometrical feature of the region that will tell us what to expect for the entropy in the vacuum state? Sorry? Yeah, the area. So we expect to have the entropy of the subsystem A at time 0 to be proportional to area of A. And this will be divided by Unicov. Okay, and at very late time, we expect that this thing will approach an equilibrium thermal state, and therefore this one expects for the entropy. And we're expecting an extensive entropy, something proportional to the volume. Okay, and now instead of being a UV scale, this would be divided by powers of beta, the thermal scale. So in between, there's some interesting thing that will happen where the entropy grows from something proportional to the area to something proportional to the volume. And this is something that really cannot be computed. It actually hasn't even been computed how this happens in perturbation theory. The one case where it's been analyzed purely in field theory is the case of a single interval in a 1+1 dimensional field theory, where Calabresa and Carty showed that this is completely determined by conformal invariance, and that what happens is the entropy increases linearly from the area answer to the volume answer, and then it saturates. In general, though, this is much harder to calculate than the two-point function, but the time dependence of this function for t less than 0, less than infinity, is an interesting probe of thermalization. How rapidly these correlations become non-local. Yeah? Could you say that again? Oh, yeah, so no, the entropy makes sense for any system, or for any state. It's just minus the trace of the density matrix times the log of the density matrix. So SA of T means the following. Because you grow A of T, that's equal to the trace over A complement of the state we have, which would be E to minus I HT Q matrix on substance K. And then we compute SA as a function of time, which is minus trace rho A log rho A. Yeah, so by entropy here, I mean the one-moment entropy, which is defined for any state. Okay. Yeah. Well, one expects it to be monotonic. Actually, one expects also that at early times it should grow linearly. Although I'm not sure that one expected that before it had been calculated using black holes. So, sorry? Yeah, but the type of function one expects for this is one expects this. I think I'm drawing the same thing. One expects something like this. That's the only answer. And here I'm plotting f of t minus s of 0. So this is the type of curve one expects, and properties of this thing, like for example the initial slope, that will be interesting diagnostics of the thermalization properties of the system. Yeah, in principle, one would like to be able to calculate the slope with a making order and coupling in a weakly coupled field theory, but I don't think anybody knows how to do that. It looks like a very difficult problem. Okay, so that's the introduction to thermalization without black holes. We discussed the two-point function, where we can use perturbation theory, or we can use exact diagonalization. We also discussed another type of growth, the quench, where you shock the system out of some low energy state to some locally correlated but high energy state, and then watch it equilibrate. Actually, I should have mentioned that for this system, you can also do numerics for spin systems. Again, for systems of up to 14 spins, one can plot this type of curve and it'll proceed along like that. Okay, yeah. Well, yeah, this is another thing that you can do to take all of the high energy state that's very, very far out of equilibrium. In that case, you might not have this feature that the entropy is small to begin with, so it depends on what the Hamiltonian was that you were using to begin with. Well, now, let me give a quick introduction to chaos. So first of all, we've discussed it so far, relaxation to equilibrium. Decay is two-point function, saturation of these entropies, but in real-time dynamics, there are also features that are growing with time, exponentially growing with time. This is something that study classical chaos is not. So in 30 seconds, what I know about classical chaos can be summarized by thinking about this classic problem. A particle moving in a stadium that looks like this. This is a classically chaotic system. What that means is that if we take a particle that say is here, and it's going that way, and plot its trajectory, plot has some kind of path. If we could displace the particle a little bit first, and then set it moving, it would have had a very different trajectory. And for this type of system, the displacement, delta x, of the particle's trajectory before and after we perturb it, as a function of time, will be growing exponentially in time, where the rate of exponential growth is called the Lyapunov exponent. So this is classical chaos. We would like to have some understanding of this in quantum mechanics. Yeah, actually, it's worse than that. This only happens for a much shorter time. This only happens until, let's say, delta x gets as big as it can. So in the stadium, delta x can only get as big as the stadium. And that will happen in a time which is like, the mod of the initial size of the perturbation, which is a much shorter time than any Poincare times. Okay. Yeah, so there was this nice paper written about this in 1969 by Blackett and Chekhov. Pointed out that you can see a version of this classical chaos in a semi-classical quantum version of the region. So what they did was they considered the commutator of a momentum operator T with the momentum operator for this particle at time 0. So T of T with G at time 0. And they argued that in a semi-classical limit, this should be equal to I H bar times the Poisson bracket. So T of T, P0. Okay? And Poisson bracket. Probably I'll have the sign backwards. Sorry. So let's work out what that is. In this case, actually only one of these terms contributes. It's the term where, it's the second term here, where the derivative with respect to the momentum is hitting this vector. That's because the derivative with respect to the position of this guy is 0. So what we get is minus I H bar times the derivative of T of T with respect to Q of 0. This is asking the following question. Suppose I take the trajectory and I look at the momentum at some time t in the future, given initial conditions. Now I change the initial position of the particle a little bit, and I ask what the new momentum will be at time t. So we've argued that these perturbations in these chaotic systems grow exponentially with the time scale set on the economic exponent. So what we expect this to be proportional to psi h bar times something which is exponentially growing. E to the lambda L times t. An important feature of this is that the sign in front of here can be both positive and negative. Momentum can be more in this direction or more in that direction, depending on exactly what initial condition we're talking about. So if we average this quantity over the thermal ensemble as it stands, we're going to get something which is zero, or at least very small. So instead what we can do is we can consider the square of this quantity, and then average it. And then the sign that appears here will always square something that's, well, actually still square something that's negative because of the factor of I. So we can consider this quantity t of t is 0 squared. And now we can average this over the thermal ensemble. Our expectation based on this argument is that in a semi-classical system, this should be proportional to minus h bar squared times e to the lambda L t, where lambda L is the Lyapunov exponent of the classical system. I'm sorry, yes, absolutely. The interpretation of this is somehow that t of t and t of 0, they all commute because we're in a semi-classical limit of this quantum system, but they don't quite commute, and that is actually something that grows exponentially as a function of time. Okay, so we can generalize this outside this single particle stadium picture to a general quantum system, and we can consider the commutator between arbitrary operators, W C, C. And it's nice to put a minus sign here to cancel the minus sign that appears there. Our expectation for this quantity, based on this analogy, is that it should grow. That these operators should fail to commute if the time separation is large, regardless of which operator D and W we started with. The fact that it's independent of which operators we have is a version of the butterfly effect, which is that, when you think about this as giving us some kind of handle on how much measurements of W at time t can be screwed up by acting with D at time 0. And the intuition of the butterfly effect suggests that any experiment at a later time t can be screwed up by any perturbation at greater time 0. So if this time t here is large enough, we expect this expression to be large. Okay. So, maybe I have time to mention that you can calculate this type of thing. Again, in the same types of systems that we've been dragging around for this whole lecture, we can think about weakly coupled quantum field theories, and we can calculate it first to leading order of the coupling, and one does indeed find that the string is growing. Or we can think about the spin systems, and we can analyze it numerically. Maybe I'll say a couple more words about that at the start of the next lecture. But let me end here and see if there are any other questions. That will take a couple of minutes. Can I take a couple of minutes, or should I discuss this at the beginning of the next lecture? Let me just, I'm very worried about the time, so let me comment on that at the beginning of the next lecture. Thank you very much. Okay. Okay, I'm really on luck. Okay, thanks a lot to the organizers for inviting me to come up here for this like second home. And also let me just give you a personal reflection. So I started organizing this school session back in 2009, and I did it for several years. Sorry, 2006. So for this I can appreciate to see that they keep on going strong, and there's so much young people interested in these people, in these topics. So I will discuss what is usually known as stream terminology. So basically I will be using all kinds of different stream tools to play with the streams and try to do something that I consider useful. And then I leave it to you just to decide whether this is useful or not. So the time of the talk is I will start today with a discussion of trying to make stream constructions. Then tomorrow I will discuss a little bit about non-perturbative aspects. Next we will move to the factory side of the story. And finally we will discuss classical applications and their applications. So let me start with the factory constructions. This time around. Okay, so the aim of this lecture is to give you some idea that if the string theory is the true theory of nature, and this is what we believe, because it includes gravitational interactions and gauge interactions in a consistent framework at the quantum level, then the string theory should be able to explain not just any gauge theory, but the standard model, the very complete gauge theory, which describes all elementary particle interactions, business gravity, or some extension of the standard model. So the purpose that I will try to follow is, first I will just try to understand the basic mechanisms that realize the interesting properties of the standard model, particularly non-abelian gauge interactions, and the existence of chiral terms. So the fact that the standard model is a chiral theory, that is that left and right partners of terms don't have possibility characters in the same way, is extremely important in model theory. And in a sense it is the only reason why we are right, and not what this is an enhanced field, basically. So once we understand these basic mechanisms, we can try to build models which are as close as possible to the standard model. And I will try to tell you how close to the standard model we can get. And you can decide whether it is close enough or not. Okay, this is a very old program, so it started in the old days of heterotic, like in the 80s with variable applications. But the program has been sustained and it's only going because as we keep on learning more and more things about the string theory at the formal level, there are more and more things that we can apply, more tools that we can apply for this model to purpose. Okay, so let's start just reminding you of the standard model of particles in case you have not seen it. And that's a pictorial picture, and let me just remind you that to this picture of forces and chiral terms, we have to add the Higgs, because now it is a true part of the standard model, and it is especially nice to say that in this room. And this is a more quantitative description with a very messy gauge sector of kind of stretchables, and a very messy sector of fermions, very messy set of quantum numbers. Okay, and the color and which interactions stage, hypercharge cycles, the Higgs contributing. Okay, you mentioned that I'm also adding like having neutrinos, just because they're very useful in model theory. They're not observed yet, but they're useful to explain theory masses, and they appear very often in this kind of string constructions that I will describe, so let me just already see them. They're just singlets of the standard model interactions. So singlets and the SU2 and half singlets after the hypercharge. Okay, let's also mention that recent things have been figured the cosmological standard model as well, that explains the history of the universe, and we understand it pretty well up to the little things which are the presence of dark matter and energy. Most of what I will share about, mostly I will focus on particle physics, and I will talk very little about cosmology, and the little bit I will talk about cosmology will have to do basically with how everything started, that is just a particular kind of models of inflation that fits well with the things I will be explaining. So mostly I will focus on particle physics. So in the string theory, because there are so many different string theories and very complicated interpretations among them, there are many different ways of approaching how to get a standard model in the string theory. And this is just one picture of different constructions that have been used. So we just focus on a particular set of models which are based on D-rays, just because they are simple. For instance, I will not say much about heterotic constructions, although they are very nice, also somehow popular as well, as you can ask me in the discussion sessions or after the lecture. I will focus on a particular set of models just to keep things focused. Okay, so this is a map of the role of things that could be discussed, and I will just try to follow a slide by. The reason to focus on D-rays is that they are simple. You just have to know how to quantize open strings, and they are also useful. They give rise to scenarios which are interesting. For instance, they give rise to models where you realize the framework idea that gauge interactions are localized with some space in space-time, whereas gravitational interactions propagate throughout 10-dimensional space-time. So this allows scenarios like large extra dimensions and things like that are very difficult to understand on the heterotic side. So D-rays are simple, and they are also useful in the sense that they give rise to models which are another very important property of D-rays is that the geometry things in a very simple way. Okay, for instance, the appearance of non-abelian gauge interactions, which is somehow tricky in the heterotic. In the context of D-rays, it's just very easy to just pile up rays and you just get non-abelian gauge interactions. Okay. So in this context, to realize the complicated gauge theory of the standard model, we just pile up rays in different ways. So to realize a U1 gauge field, you just put a single ray and do something like electromagnetism. If you want to work on your color, you use 3 rays on top of each other, so you have 9 open space sectors. So basically you get some SU3 like structure and some U1 factor, which we will discuss later on. There are plenty of U1s, and there is a lot of bridge physics of U1s that will be one of the main topics of my talk. To reproduce electromagnetic interactions, you just put 2 rays on top of each other, and there you have electromagnetic